more than what school teaches us. And today we're going to have a guest from India. Her name is Medha Bansal. Is an emerging technologies and design graduate at the Architectural Association in London. Her dissertation work investigated the material system and fabrication mechanism for ecologically adaptive and climate resilient construction in their desertification-prone regions. Medha is also dedicated practitioner of architecture, currently working in New Delhi, India. She has experience in commercial, residential, and cultural projects across a variety of scales. In 2017, she completed a certification course, Master in Parametric Design from Madrid. Prior to the AA, Medha received a Bachelor in Architecture from Sushant School of Art and Architecture, where she served as a research assistant in her final year. Her graduate thesis at AA was awarded Exemplary Project of Academic Year 2019. Currently, her interests lie in the application of advanced computational design and fabrication technologies within climate-conscious architectural practice. Thank you very much for accepting our invitation, Medha. It's a true honor to have you here. I know it's early in the morning there, so thank you very much. And you can begin whenever you're ready.
Yeah. Yeah. Thank you, Isaac. Thank you for that invitation and giving me this opportunity to present my thesis. So good morning to all. It's early in India, so good morning. And I'm really glad to share my graduate thesis in Dune with you all. Like Isaac mentioned in my introduction, I'm an architect and a computational designer, and specifically interested in designing for climate sensitive regions of the world. So my thesis in Dune looks into the problem of desertification. So for those of you who are not well versed with the term, desertification is a form of land degradation in dry and semi-arid regions of the world where the land loses its biological productivity due to human activities like um, uh, bad agricultural practices, deforestation, and natural processes like extreme weather conditions and drought. UN in 2014 declared desertification as one of the extreme environmental issues of the century, and has projected that by the end of the century, 1/3 of the Earth's land could actually turn unproductive. So for our thesis, we primarily focused into the world's most populated desert, the Thar Desert. Thar Desert constitutes the northwestern part of the Indian subcontinent, where it is exposed to, where 76% of the land is exposed to wind erosion and sand deposition form of land degradation. And within this region, our test site that we chose is subjected to extremely high wind erosion index, which means that the strong winds blowing in the region makes the terrain absolutely unstable. There's a constant influx of sand into the region, and there's a constant dissipation of sand out of the region. So if you see it on the diagram on my left, towards my left, you'll see that because of the strong winds, there's an array of linear dunes in this region, which becomes like a test module to explore computational approaches towards anti-desertification. Using Landsat imagery, when we further zoomed into the area to see if there are possible settlements, we saw these mushrooming small settlements within the region, which are mainly housing the interdunal plains. Now, what happens in these interdunal plains is the wind velocity drops, and that is where maximum sedimentation takes place. And by Landsat imagery, we realized that all these settlements were actually just informal settlements, rural areas, decentralized villages, which lacked infrastructure. And also because there was a serious dearth of information that we could find, we actually made a visit to the site to see what are the ground realities. And to my shock, I mean, we found that the weather conditions and the living conditions are so extreme that it doesn't even support the life of livestock. The infrastructure is still very primitive and vernacular. The terrain is absolutely unstable with constantly changing and shifting grounds. And even the existing infrastructure is subjected to heavy sedimentation. Like towards my right, these are the houses which were completely submerged under the sand. And this was the only road leading to this remote area of the country, which was again absolutely covered with this constant influx of sand. And people had to manually remove the sand from this region. Another observation that we made during the site visit was that there's an absolute shortage of water resources and a significant absence of green cover in this region. So this made us ask a question that how can we tap into some stand stabilization techniques and redesign the settlements in this region. And when I say, I mean, when we were asking this question to ourselves, we always kept at the back of our mind one thing, that whom are we designing it for? Our idea was that since the people inhabiting these regions are locals, are migrants, are mainly agriculture practitioners, these people are well versed with the textures, colors, and materials of that region. So whatever proposal we propose, whatever proposal we come up with, it has to come from the site. We cannot immediately propose something which is very alien to these people. And this image that you see on the side is sort of our first design ambition. I mean, it's not a design outcome, but it's a vision that we had for the site, for these people, where a system could be generated where water, agriculture, and habitable spaces could come together and exist in synergy. And at the same time, the terrain, which is so highly unstable, can be stabilized, which could facilitate the flourishment of these systems. And at the same time, a natural mechanism is induced where the influx of sand is naturally deflected out of the system. So these were our prime goals when we went into the research part of it. So my main research area for the thesis was wind deflection system, material system, erosion measures, and agronomics. And when we were looking at ecological measures, we were very conscious of creating a mixture, an amalgamation of existing and modern mitigation interventions. So the erosion control systems and the wind deflection systems are primarily the traditional systems which are still followed into the area. And we specifically wanted to focus on new building material system. Now, looking at the site, we kind of made a shift at looking at the problem. The abundance of sand and the influx of sand was suddenly a resource for us. For sand could be used as a new type of building material if combined with a proper construction binder. So we looked into the technique of biomineralization. Now, biomineralization is an existing technique which is investigated by a lot of material scientists, engineers, and architects, where if you take sand and add biopolymers to it, the biopolymers form a gel matrix in the sand and kind of create a really strong material with high compressive strength, to the point that its compressive strength is comparable to a concrete block. But at the same time, it has a lot of ecological benefits, for it is absolutely biodegradable and has almost zero carbon footprint. So to explore this material system in context to our site, we looked into the biopolymer of sodium alginate, which is again readily available from the vicinity areas of the site. And we looked into how we can develop a composite material system out of it. So now if you mix this biopolymer into sand and add calcium to it, you essentially get a composition of a sandstone. And if you look historically, all the monuments, at least in India and specifically in this region, have been standing there for centuries. And the prime composition of the material of these heritage buildings are sandstones. So in a way, biopolymerization helped us to attain a very strong material with compressive strength comparable to a cement block with lower carbon footprint. And also it attains, the curing time is almost half of that of a cement block. Then we further wanted to investigate if there's been a study or any ongoing research on the fabrication mechanism of biomineralization. We came across this really interesting study carried out at U Delft with other institutes, that where they explored biomineralization and scalability. So they tested the hardening of sand, the volume of sand for different volumes, using dry mix and cast method and using injection method. So essentially you have huge volumes of sand and you inject your biopolymers with biogrouting. And the results were pretty comparable in the sense that biogrouting is an efficient way to scale up this technique. Even though the homogeneity of the sand mixture reduces as you scale up, but with increased density of injections, you can get more homogeneous and compact sand. So this suggested and gave us a hint of how we would want, what fabrication mechanism we could explore to develop our site. For stabilization technique, like now that we had a material system and a fabrication system, I mean the ideas of it in place, we really had a vision for the site that we wanted to use this material system to stabilize the existing sand and convert it into agricultural terraces and Indian structures. And at the same time, for the incoming sand, we wanted to deflect and automate the deflection of the incoming sand using the wind itself. Like in the region at the beginning of the presentation, I showed you the picture where strong winds are bringing in the sand. But we looked at the strong winds as an opportunity to take the sand away from the system. And at the same time, once we have these three things in place, we could bring water and agronomics back to the equation and create a holistic developmental plan for the site. But before we proposed that, it was really essential for us to understand the dynamics of the region, that how the wind brings in the sand, from what direction, what are the velocities across a dunal section, and what's the net sand transport direction. So the sand is predominantly getting winds from two directions, and the resulting vector makes the site transform into this array of linear dunes. And also because of the bimodal wind, the site gets divided into windward and the leeward faces. Now again, because of this, I would say the shape or the section of the site, we see a varied pattern in sedimentation, where maximum sedimentation happens on the dunal crest and least sedimentation happens in the valley, where the strong wind vector filters away the sand in the valley region. Now going further to biomineralization and taking inspiration from the experiments done at TU Delft, we proposed our own mechanism where we selected a machine which could run over the dunal fields with a matrix of injections and inject large chunks of the land at the same time to accelerate the fabrication mechanism. So we selected a machine which had a dimensional constraint of a jig of 3 meters by 3 meters. Now, these constraints were really important for us because these constraints slowly started to define the morphological sizes and volumes of spaces, which you'll see in the further slides. The mast of this machine could travel up to the depths of 15 meters and inject the biogrout. So in volume, you can basically generate a volume of 15 meters of hardened sand mass. Now, the picture on the left shows that how the machine is efficient in traveling over the dunal fields and injecting at different depths. But the existing dunal slope was greater than what the machine could withstand. So we also proposed manual flattening of the dual slope wherever we wanted to inject the biogrouts. And, uh, and for that, we needed additional ancillary machine support, where just like how you do construction mountainous regions, you have sheet piling, you remove the excess uh, sand to kind of flatten the dual slope, and then you inject and at the same time excavate the unhardened sand. So our next course of action was to develop a toolpath for a machine. Now, for developing the toolpath, we wanted a compact packing of those hardened 3 meters by 3 meters plot, because in separation or in over injection, there is loss of material, and in separation or not so compact packing of 3 meters by 3 meters hardened patches, the subsoil remains weak. Also, we had the objective that since the machine has the capacity to rotate from the at the same position and inject at multiple sites, so it should do that in order to reduce the time lost in parking and then injecting. And at the same time, the toolpath should be such that the machine does not overrun the pre-hardened surfaces. Now, if the machine were to run in XY plane computationally, it could come up with like zillions of, almost infinite possibilities of toolpaths. So we narrowed down, we wanted to see that what type of curve or trajectory type could we select where the first two objectives are inherently met. And we observed that on toolpaths based on 1 degree curve could actually inherently avoid the problem of overinjection and gaps between these hardened patches. So we wrote several algorithms based on machine's position as inputs and came up with over 200 toolpaths. I'm just showing a few of them on the slide here, which shows how the machine, from its different properties of rotation and injection, could come up with several toolpath options. And we select a toolpath which has zero gaps and zero overlapping patches. The selected toolpath has a spatial constraint of 12 meters, and it could inject one single block in a day, considering that the machine runs for 12 hours. And it takes 6 hours for the machine to inject the biopolymer and 6 hours for calcification. So we projected that in a day, the machine could inject one block. And and keeping this time frame in mind, we thought that the site would take approximately 20 years, that is a stretch of 1.5 kilometers to develop. Of course, we revisited this time frame as and when we further detailed and integrated our different systems into our fabrication mechanism, which you'll see towards the end of the presentation. With this fabrication mechanism, we realized that the machine has the potential to harden different profiles and induce different functions. For example, the ability of the mass to travel up to the depths of 15 meters could actually facilitate multi-level profile. Um, Also, the material is hard enough for, with the diamond cutter or with any cutter, we could give it a particular shape for aerodynamic reasons. And also we could excavate the unhardened sand and fill it with fertile soil to promote the growth of plant species. For site profile development, there were mainly 4 things that we were looking at: terraces for sand stabilization, sand channels and wind deflection systems to take care of the incoming unstable sand, and in-dune structures. I'll be talking about each one of them in detail in further slides. So now first talking about terraces. Now, transforming this tunnel section into terraces was not really an intuitive design decision. It came after the observation that the site has basically no texture because of vegetation. It was a barren piece of land. And because of that, there was no cell shading property, and the land, both in summers and winters, was exposed to high solar radiation. So in order to reduce the solar radiation, the most obvious step we thought was we had to introduce surface texture. So adding these terraces was the most obvious choice for us, that we wanted to develop these terraces. And to develop these terraces, we used the computational methodology of multi-objective optimization, where our objective was to generate a series of steps on the side such that each step had enough width to accommodate habitable spaces. It could also cater to our first like prime objective of self shading, but at the same time, for easy circulation, had minimum height differences amongst them. So a lot of these criteria were kind of contradicting, and for which we use multi-objective optimization as a tool to get a series of different morphologies of these steps. But we observed that there wasn't any significant or radical difference in morphology of terraces that we got. So then we ran a second series of tests, a shadow analysis, to study which of the morphologies suited best or provided maximum self shading. And we selected a patch which did that for us. And this became our overall morphology for the site. Furthermore, in order to zone our programs of agriculture and habitable spaces, we saw that for the hottest hours of the day, that is from 11 a.m. to 2 p.m., which side of these terraces get maximum self shade. And we realized that the windward phase gets maximum self shading, so it becomes suitable to zone our habitable spaces there and agricultural spaces on the leeward side of Dune. Moving on to to talk about sand channels. Now, while the terraces took care of stabilization of the existing sand, the unstable sand, sand channels basically took care of the incoming sand. For that, we looked into the principle and the physics of sand, that the sand particles are automatically moved or displaced from a surface if the wind velocity achieved is 6 meters per second. And in a bimodal wind direction, the wind coming from this direction is the strongest. So our idea was that we create certain ditches onto the site where the incoming sand from the west, it drops the sand into these ditches, and the sand blowing through these ditches, because of Bernoulli's principle, it kinds of accelerates and takes the sand away from the system. So it's like a natural cleansing for our site. For this reason, we created a matrix of sand channels that based on a machine's constraints. So a machine could inject maximum volume of 15 meters by 15 meters, as I mentioned earlier. And we gave an input velocity of 4 meters per second to see in which sand channel does the speed get accelerated and attains a target velocity of 6 meters per second. So we observed that there were certain combinations of these sand channels that I've marked in red that actually achieves this objective of accelerated wind velocity, which helps in taking the sand away from the system. And qualitatively, we realized that as the sedimentation is highest towards the crest, the bigger sand channels should be distributed more towards the crest, and the smaller channels should be located more towards the valley. I'll come back to the wind deflection system after I discuss the in-dune structures. So this question was asked to us by a lot of people, that why are you building in-dune structures? Like, you already have this technique of biomineralization, and scientists have proven that biobricks are highly compressible, have high compressive strength, and they work. Why do you want to build in-dune structures? So our answer was that in-dune structure actually helps environmentally a lot in this region. For there is a heat exchange between the subdunal soil and the structures, which can automatically reduce the temperature to a great degree. Secondly, the winds blowing in these regions are so hot and are loaded with sand that anything you build lower the ground, you're essentially avoiding the exposure to these hot winds. So for these two reasons, we wanted to build these in-dune structures. And furthermore, for building in-dune structures, we had to make a radical shift in the way of structural thinking from prefabricated uh, form of construction to more into granular cementation of the sand. By that, I mean that we proposed bio injection of our biopolymer within the grid of 3 meters by 3 meters. And with a matrix of injection, we proposed that, you could cast your foundations. With single point injections, you could cast your monolithically cast your walls. And once you have this hardened profile on the ground, you could excavate the unhardened sand and stack it up with secondary material, which could again be locally procured, and create these cavities or excavated pits which are ready to be inhabited. For this, so once we had this sort of a mechanism in place, we wanted to divide our leeward side into colonies or clusters where our habitable spaces could finally come. And based on the urban design principle of walkability, based and also based on sedimentation pattern, we sort of subdivided our plot ranging from 75 meters to 200 meters. Now, to develop the morphology of in-dune spaces, we conducted 4 experiments. The first 2 experiments facilitated the other 2. So here we wanted to understand the orientation or global orientation of our machines such that once the pit is excavated, it can naturally cast maximum shadow, it could cast maximum shadow in itself. And we realized a 30-degree global orientation did that. Secondly, it was a hypothesis that building in dune could reduce the temperature, but we actually wanted to note that how much of a temperature drop are we getting. And we realized that when the outside temperature rises up to 50 degrees Celsius in summers, you can actually achieve a temperature drop of 20 degrees Celsius inside these pits, where the temperature starts to equalize after 9 to 12 meters, which means you don't have to go all the way to 15 meters down. You can limit your construction to 9 to 12 meters and have a reduced temperature of 30 degrees Celsius. Now, 30 degree in itself is a high temperature, but for a region which has temperature as high as 50, a drop of 20 degrees Celsius is really, really significant. So for developing the morphology of our habitable spaces, we split our experiments at 2 stages. The first dealt with the planar aggregation of spaces, essentially how we would generate a plan. And the second dealt with the volumetric assembly of these spaces. I'm going to first explain the planar aggregation of programs. So based on site visit, we created a matrix on what all the functions are required by what family sizes. And we translated this data computationally into cells, where each cell stored the information of family size, the number of units of functions that it needs, the hierarchy of occurrence of these functions, and also certain adjacency rules between these functions. And in order to simplify it, we categorized our functions into primary, secondary, and tertiary categories, where courtyard spaces became the primary functions around which all other spaces would aggregate. So in multi-objective optimization, we would say these became our gene pool or genes, and with our rule set of aggregation that suggests where we set the rules related to zoning, orientation, and connectivity between these spaces. So the primary the primary, secondary, and tertiary functions were essentially had the spatial quality of being open, closed, and semi-open spaces. So we wrote our first multi-objective optimization script with the objective that we wanted our spaces to be arranged in such a way that they have maximum perimeter to facilitate heat exchange. Certain spaces like bedrooms and nurseries should have particular quality of space, as in terms of reduced solar heat gain. And there should be an increased social fabric within these spaces. So how we wanted maximum connectivity between these units. Based on that, we ran this optimization script, which gave us multiple planar aggregation of functions. And we selected our phenotype or the design outcome based on the criteria that whichever configuration shields the open spaces of our courtyards naturally by populating closed spaces around it, we would prefer that. And also whatever configuration gave us maximum coherency of units for enhanced social fabric, we would select that phenotype or that design outcome. Moving on to the second stage of morphological development, we wanted to now see how these spaces could translate into actual volumes and be arranged in space. Now, the microclimate analysis, which I showed you a couple of slides back, where we saw that temperature drop of 20 degrees Celsius, actually helped us to stratify these functions in section based on their requirements. For example, bedrooms being the most critical spaces were preferred to be located at the depths of -9 to 12 so that they are more thermally comfortable for inhabitation, whereas living spaces and kitchen could have relatively higher temperature. And once we had set this experiment, we wanted to evaluate design options based on criteria where we could have minimum excavation, there could be easy circulation, and at the same time, there could be maximum surface in contact with earth for heat exchange. And at the same time, the configuration should enhance self-shading. So this script of spatial aggregation of programs essentially showed us how our spaces are coming together in volume and in section, and how we are getting these different qualities of open, closed, and semi-open spaces. And further, to select the design outcome, we ran another set of tests which suggests where we picked up the design outcome where the roofs had least solar heat gain. So because the roofs are the main architectural element which are responsible for heat gain, we selected the one where the average radiation or the total radiation was least for amongst all the morphologies that we got from this experiment. And this is a sort of like a visualization of how we imagine the spaces, walls, and floors to come. So if you look at the -9-meter level plan, all our habitable spaces, that is bedrooms, all these spaces can be seen at this level with nurseries, and at a higher level, all our living spaces, kitchen, toilets, are at the upper level. Again, as we did a qualitative assessment of how our courtyards would be distributed along the site, where maximum or the bigger courtyards are suitable for the regions which have least amount of solar exposure versus versus courtyards with small courtyards to be given in regions which have maximum solar exposure. Now, now that we have in-dune structures in place, we have sand ditches in place, there's always I mean, the sand could drop, the wind that carries the sand could drop the sand either in these in-dune structures or in these sand channels. So how do you make sure that the sand is not dropped in these in-dune structures, but is actually deflected towards the sand channel and through which it is moved out of the system? For that, we needed a wind deflection system, which essentially became a roof structure for us. And for this roof structure, we also needed to comply to certain criterias. For example, the high wind speeds uh, in the region forces a lot of wind load and lift forces onto the roof. So it should be able to withstand them. And at the same time, it should be oriented in such a way that it can deflect maximum sand into these ditches or sand channels. So for that, we did a primary study of of different shapes of these roofs, like which shape is more suitable for these roofs, and we tested them for criterias like minimum reduced turbulence zones, maximum region with reduced velocity, both in section and in plan, and also the surface which could show structural performance. And based on that, we realized that the pyramidal roofs work best for us. And within the pyramidal roof, an inclination and orientation of 30 to 20 degrees and an orientation of 130 to 135 degrees in plan is highly efficient in deflecting the sand into the pit. Now, again, once there was also, since the wind loads are so strong, there's also an upward thrust that comes. So it was essential for us to introduce openings into our roof structure to mitigate this wind lift. And we realized that a uniform density of openings actually mitigates the wind lift by 61%. Further, we wanted to, like I said, that we wanted everything to come from the site for the site. We wanted to develop a material system based on all the materials that were available to the site, and we selected them by generating this 4D evaluation matrix, where we tested different material combinations for roof spans, lifespans, thermal conductivity, and their distance of production from the site. Based on all these criteria, we realized we want a roof system where we have its structure made of wood and it is cladded with fiber reinforced sand and biopolymer tiles, and the biopolymer being sodium alginate, which we are already using to transform the terrain and generate Indian spaces. Furthermore, we also wanted to know that what are the structural system that the roof should have. So based on that, we did a market survey on what are the available wooden member sizes and how they can be arranged such that they perform structurally for predominant wind loads, for wind lift forces, and the dead load of the structure itself. And for this, and based on these criteria, we ran a series of structural tests which suggested and told us that roof spans beyond 18 meters did not function well structurally. So we had to limit our roofs from 3 meters to a span up till 15 meters. And again, qualitatively, based on sedimentation, these roof spans linearly increased from valley to crest, sorry. And that led us to write a final multi-objective optimization algorithm where we wanted to test our roof aggregation such that it could direct maximum sand towards the channel. It could also it could also let a lot of indirect sunlight come into our excavated spaces, but at the same time could maximize the shadow on open spaces. And then we ran our series of tests for this experiment, and we got several over 900 configurations of roof aggregations and studied how they're deflecting the wind, and prioritizing the objective of maximum deflection and reduced wind velocity in the lee side. We selected an aggregation of roofs for the site. This once so now that we have our terraces, sand channel, wind deflection system, and Indian spaces in place, we now be looking at the cluster time scale, that how on from day 2 we start getting our machines onto the site, how from in 45 days we start injecting these spaces, and how in 2 months, in a period of 2 months, we start excavating them, laying our additional stacked floors. And within 3 years, this cluster slowly becomes habitable, where you can see different spatial qualities of large family units, medium-sized units, small family courts, with a roof system over it, and nurseries, and a protected environment and nurseries for plants to flourish. And within 10 to 20 years, the spaces are further excavated and used for human use as the population grows. Um, while this was an intra-dunal section, this shows how we imagine our different spaces to come at different clusters coming at different steps. And this is how we essentially visualize our spaces to be. The, like the surface textures and how people would inhabit these spaces. Um, I agree that these are just visualizations, and obviously there'll be a huge difference when we actually do biogrouting on the site. So for our, this was a comment that we kept getting for our thesis, and I would like to mention it here itself, that we could not conduct any physical prototyping for this sort of architecture because it is very site specific. The experiment, how much your biogrout spreads onto your site, is very site specific. So whatever we proposed so far is more like a theoretical framework, but instead of looking at it as an end product, I mean, one should look at it as tools, as means that we've produced to generate a morphology, an argument of spaces that can come in this climate sensitive region. And of course, the surface textures and all will vary based on the physical experiments that would be conducted on the site. Now, moving on, I mean, I'm going to go through this section of the presentation real quick. We move to the productive systems. Now, this is a vision that we had for the site, where once we have a deflection system, a habitable spaces in space, how we merge it with the existing techniques of plantation and the erosion measures that are discussed briefly at the beginning of the presentation, that how we have our agricultural terraces, an integrated hydrological system in the scheme. We actually calculated the crop volume that we need for a target population of 2000, over 2000 people. And based on those calculations, we realized that a stretch of 200 meters of the site, basically this becomes self-sufficient, that the amount of people inhabiting a stretch of 200 meters would require the agricultural area that comes within the stretch to sell to be self-sufficient, and which gave us a phasing strategy for the site, that the site needs to be developed in phases of 200 meters in development. And based on these calculations, we revised our global time scale, and it suggested that the site could be developed in 27 years. Moving on to the hydrological scheme, we looked into the existing resource of artificial irrigation canals, aquifers that are present on the site, and our proposal to collect surface runoffs. We looked into the treatment of these waters, of the different qualities of water, like each source had different levels of contaminants of different qualities. And we wanted to tap into the excessive solar power in this region, the sunlight that we get to perform solar desalination. And we also propose bioremediation to purify this water and use for agriculture uses and for people for domestic uses. Here is a view how we designed the our hydrological channel, such that it is functional for the three conditions: under normal water level, where second, when there is a shortage of water, and the condition when there is flooding of water. So we have these three levels of reservoirs which replenish each other under any of these conditions. And this is how we envision our hydrological treatment and distribution, that close to the hydrological system, we have our public spaces. And once we have these public spaces, that is after we have these public spaces is when we have our agricultural and habitable spaces coming along. We did an investigation of how shelter belts would actually deflect the sand from a system, and we realized that uh, a combination of shelter belts and the sand channels that we proposed on the site actually deflects the winds outside the system, increasing the sedimentation on both the sides, but outside of our terraces. We also did a study of what all species of shelter belt plants that would be required, how they will be arranged onto the site, on what slope gradient, and based on their roots and their dimension, what are the ideal sizes for the terraces for shelter belts. We also looked into the types of crops that are needed for the region, such and we proposed practice of crop rotation, agroforestry, and and how these crops could be distributed based on their seasonal requirements and solar radiation available on each site, and how they should be combined with the existing vernacular techniques to save the water of like half moon pits, ridges, mulching, and bunds. Again, this is a view of how our different qualities of species are coming together, and how within these sand channels and water channels, we practice micro irrigation within the system. And to tie it all, and how all our systems are coming together. So initially we have these wind deflectors which deflect the wind outside the system, and we have these mats that kind of stabilize the terrain, and how we have slowly we bring water into the site and lay out these ramps and maintenance sites for our machines, and how slowly in 10 years time 2 phases could be completed, and agriculture and infrastructure can start coming together, and how in 50 years of time span can the entire site be developed, and how multiple settlements can come together um, within this entire region. And to conclude, I would say that these multiple settlements, because the sand because our mechanism throws sand outside the system, these multiple settlements need to come in stagnation. And also, there's a lot of potential to take the study further and develop it for road networks and inter-settlement social fabric, and at the same time explore other sources of energy that are available on the site, like wind and solar power plant for regional development scheme. And this is how we envision our site to be. Yeah, that's it. Thank you.
Thank you very much, Medha. That was pretty amazing, pretty interesting. Thank you very much for sharing that. Um, so we open our Q&A session. If anyone has any question, please raise your hand or write it down in the chat. I have a question. You were talking about a multi-objective algorithm.
Yeah.
Which one was it? Was it like Wallasey or?
Yeah. So we used Wallasey for running all our multi-objective optimization scripts.
Awesome. There's another question. Rodrigo, do you want to turn on your microphone and do the question yourself?
You're on mute.
Can you hear me now?
Yeah.
I was actually going to make the same question, like what was the tools you use I mean, but not only for multi-object optimization, but for the entire thesis.
So we split our experiments at different levels, right? For wind analysis, we used Autodesk CFD to study all the wind behaviors. For multi-objective optimization, like I mentioned, we used Wall-E. For environmental analysis, we used Honeybee and Ladybug. So yeah, these were the main softwares that we used.
Thank you. I don't know, like I know there are a lot of students, architectural students around here. So I don't know if like there's any suggestions or advices you would like to give them once they are looking for a
Yeah.
master degree.
Yeah, so one of the greatest learnings that I found during this entire procedure was like a computational learning that I had. That when you have a complex design problem, when you have too many things to handle, it's always better to break down your experiments into smaller experiments. Like for us, we knew that we wanted to develop in-dune spaces, but we did not straight away jump into it. We divided our experiments into multiple experiments. Like first we generated a planar aggregation of spaces, which helped us deal with a lot of spatial quality issues. Then when we moved on to the volumetric experiments, it helped us to deal with environmental problems like self-shading, and also helped us to propose something more efficient way of construction, like minimum excavation, easy circulation. So it's always better that, you know, when you approach design problem, you divide it into multiple experiments and then bring everything together towards the end. And that way your design solution will be much richer, for it will have more embedded and in-depth solutions in it. Yeah.
Awesome. We have another question in the chat. Says, excellent presentation. Thank you very much. Did you use any software for the structures?
Yeah, sorry, I forgot to mention that. We used Karamba to study, to do structural analysis. Yeah.
Nice. Thank you. Si alguien tiene una pregunta en español, puede hacerla y tratamos de traducirla. La pueden escribir igual. La gente que está en el Facebook Live, igual puede escribirla en español y la traducimos. Okay, I have another question, probably out of topic. I know that you studied at Architectural Association.
Yeah.
Some of us have like this doubt about where to study the master. So why did you pick the AA?
Okay, for several reasons, that particularly MTech, because you know, often when we get into computational designing, we often lose the sight of you know, who we as architects are, what's the purpose of it. And we really get into the fancy aspect of using these tech, you know, these high-tech fabrication mechanisms and the tools that we are offered now. But MTech in specific is one course where we integrate computational designing and architecture really beautifully, in the sense that my thesis, if you look at the design outcome, I mean, by the looks of it, it is native to the site. It's not out of, out of the context, or it is something which people can relate to, but at the same time is strongly based on computational evidence. So for this reason, where we could find a sweet balance between computational designing and architecture, I specifically chose this course. And I have like a lot of friends who've already did this course, so I knew about this course well in advance, and that's why I went ahead with it.
Awesome, thank you.
Yeah.
Okay. see if we have another question on Facebook. I think no. Okay. I think there's another question there writing it.
Yeah.
Okay. I think they haven't finished writing it. I have another question.
Yeah.
There it is. It's in Spanish though. It says, how do you feel working with digital technologies in I don't know the English word for that. Just one second. O sea, cómo usar herramientas computacionales con arquitectura vernácula o en zonas rurales.
Ah, te pasaste con el término. I mean, the question is kind of like, how do you mix digital new technologies with techniques that are originally from the site, like traditional, more handcraft techniques maybe?
Right. Okay, I got the gist of the question. So basically, you draw from the principles of the existing site. For example, like shelter bells and the other geomats that we looked into, we essentially realized the principle that what they're doing is they're reducing the wind velocity. They're reducing the wind velocity for us, and how we could translate it digitally. Secondly, you could look into I mean, you can combine digital techniques with local materials. That is another approach towards it. For example, in our thesis, we essentially did not use any material which was outside of the site. We used everything that came from the site, and we just combined it with um, a different approach of fabrication. Even the fabrication mechanism, it's a simple biogrout machine which is available and essentially used at every construction site. It's not a robot that you need. So it's really a make like a shift that you make in your view, how to see, how you see at the how you look at the problem, and how you adapt the solutions and just use it in a smarter way. I hope that answers that question.
Yes, I think so.
Yeah.
Okay, I think there's another one. Yeah, you want to turn on your microphone?
Sorry?
Yeah, there's another question, but we're waiting if she want to ask herself. Go ahead.
Okay. Do you hear me?
Yeah.
Oh, okay. So my question was, did you have the opportunity to talk with the people in the existing villages for some feedback about your ideas?
No. So when I did the site visit, we had the opportunity to talk to them in depth about their problems and how they are in day-to-day life dealing with desertification, a problem like desertification, which inspired us to form our design strategies. And yeah, so we didn't have a chance to, I mean, actually, it's a very good point. And now that I think about it, it should be done because they should be made aware of the proposal that we made. Yeah.
Hope you have some time, maybe in the future.
Yeah.
Thank you for your talk. It was very inspiring.
Thank you.
Okay, there's another question. We have like a private chat. They are asking there. If you use any kind of a script for this project, maybe Python or something.
Yes. So when I was writing multi-objective optimization for planar aggregation, I used the concept of Celer automata. And for that, I used Python scripting in Grasshopper. So yeah, I did do Python scripting for that.
Awesome. Yeah, I think that was another question, but I think you already answered it.
Mm-hmm.
Okay, so there was like a lot of technology applied to this project, even though it was like rural. I think that was the other question. So do you think in the future this would be like a regular approach to projects on these kind of sites? I mean, it kind of looks like a lot of technology for probably something that it's not used to that technology.
Yeah,
That's
actually,
like
it's a good question. So I really feel that in regions like